Previously on Secrets of Calculus.
A brand new game show. E to the E to the E to the X. Now it just finds the X and Y squared and... Welcome back to the Secrets of Calculus. Today, we will finally, at long last, get a flowchart for solving derivatives. Oh, hang on. Is this video too long for you? Don't worry, this is just a specific case of chain rule. Let me know what you did with that extra free time. Before we make a flowchart, we need to address exactly what came up at the end of last episode. Non-functions, like x squared plus y squared equals 1. This equation here plots a circle of radius 1 with its center at the origin. Since it's not a function of one variable, we can't just take the derivative and get the slope of the tangent line. But we also don't want to solve for y. This all works based on the chain rule. We should first take the derivative with respect to x of the whole equation so we can narrow down to the trouble spots. Okay, there's our issue. There are no x's to be found in y squared. Now what we can do is trick the derivative into thinking there is one using the chain rule. Remember this form of the chain rule? We're going to do exactly that, but instead of u, we're using y. How is this helpful? Let's think back. Functions like f of x equals 3x can also be written as y equals 3x. And when we were first defining the derivative, we were finding dy over dx, the slope of a tangent line. There we were, treating the fraction slash operator dy over dx as a variable whose value happened to depend on x and y. So now, if we wanted to find the slope, we can treat dy over dx as a variable and solve for it. And there we go. Believe it or not, that is our answer. Plug in any two x and y values on the unit circle, and you get the slope of the tangent line. Here, I'll prove it. At x equals 0, you get a slope of 0, which corresponds to this instantaneous flat part of the circle. At y equals 0, you get a slope of dividing by 0, which is the undefined slope, which corresponds to this instantaneous vertical part of the circle. And now, at a tamer point, like, say, square root of 2 over 2 and square root of 2 over 2, we can plug them in to get a slope of -1. And would you look at that? The tangent line at that point on the circle has a slope of -1. This technique right here is called implicit differentiation, and it works as long as you can solve for dy over dx, which most of the time you can. This is literally just chain rule being used like it's on steroids. Alright, let's now put together a flowchart to solve all derivatives. At any point, you can do some algebra to clean up any messes that come up. So, this flowchart is nice and flexible. Step 1 is to distribute the derivative through addition and subtraction and move any constants outside each derivative. Step 2. Apply the product rule, quotient rule, and chain rule wherever it's applicable over and over and over until you get down to a basic function, like e to the x or x squared or something like that. And this is also the step where implicit differentiation is used. Step 3. Use the big brain rules on derivatives of the basic functions. These are the power rule, where constants turn into 0, x to the a turns into x to the a minus 1. You also get e to the x that stays as e to the x. Natural log of x turns into 1 over x. And
The square of
comes into play. Seriously, that's it. 3 steps to solve pretty much every derivative you will ever encounter. And with that, our Alpine Slide is completely fixed. It will be both safe and fun. We can put smooth parts for the start, make a smooth end, and even put in a loop-de-loop if we wanted to. At all times, we know exactly how fast the sled is going. Now, I say pretty much every derivative you will ever encounter, because there's always going to be oddball functions that don't play nice. For example, absolute value of x has a spike at x equals 0. Where would you even put a tangent line there at x equals 0? the derivative is actually not defined at x equals 0. So while you can take the derivative of the positive and negative sloped parts, you can't find the derivative here at x equals 0. So that sucks. This also means you have functions like the Weierstrass function, which is continuous everywhere, but it's nothing but spikes, so the derivative is undefined on the entire function. Here's what that function looks like. Yeah, it's pretty weird, and it completely upended mathematics when it was first discovered in 1872. Wild. So goodbye, limit definition. We don't need it anymore. But that's not to say limits are useless now. In fact, next episode will be about how the derivative can help out the limit, and we can finally compute some of the limits that we were brute forcing before. See you next time!